Welcome to this video. My name is Mark Scythian. The date today is October 3rd, 2024. So this video is going to focus on the wave-particle duality and a practical application. So this is obeying the conservation of energy. And so here we are, we're equating a rotating mass, let's say it's a flywheel, or it even could be a subatomic particle, and it functions as a particle, but if we had its energetic equivalent, we'll just say it's electrical sinusoidal wave. Let's say it was a radio wave oscillator being powered by a signal generator that's purely mechanical. So we have 360 degrees to rotation, but with respect to radians, every 1 pi radians is 180 degrees and 2 pi radians is 360 degrees. So when we quantify angular velocity, it has to be with respect to the radians rather than the degrees. So assume that we have a alternator connected to a drive shaft or a flywheel on an engine. And so we'll call that the particle mechanical. And the goal is to convert the motion into an energetic signal or a wave. So we'll call that electrical. And so this is a practical application. Now, this is a fundamental that can help the student or the project developer transcribe the relationship between mechanical and electrical, or the particle and the wave. So assume that you needed information about the RPM, the torque, the total brake horsepower, the mechanical wattage, etc. So essentially you were able to convert an alternator into a brake dynamometer for, let's say, engine metrics testing across different RPMs. So assume we start at 600 RPM and then we gradually increase the RPM to 2000 RPM. So this implies that 600 RPM is 10 revolutions per second. And so if we look at one revolution as 2 pi radians, 360 degrees, we have 10 times 2 pi, or 20 pi radians per second for 600 RPM. And 2000 RPM, we divide it by 60 seconds, 33.33 revolutions per second. So 33.33 times 2 pi is 66.66 pi radians per second. So if we look at one cycle of a sinusoidal wave or sine wave, this would complete 1 hertz if the time period was 1 second. But based on these RPMs, the frequency is going to be 20 of these cycles per second for 666 of these cycles per second. So we can then make the scaling factor for 600 RPM 1/20th of a second, or a time period of 0.05 seconds. So that's written here in purple. And then 166, and of course it's been rounded down. It should be 67, but we'll just demonstration 166, 1 over 66.66. So it's approximately 0.015 seconds time period per cycle at 2000 RPMs. So we've succeeded in if not converting one type of energy to another, mechanical to electrical. But perhaps we'll use the alternator as a sensing or a sensor device, so we can get the information of what's going on with this rotor. So at 600 RPM, we know there is 20 cycles per second, and assume that this alternator is without the diode and without the voltage regulator. So it's really an AC generator, not an alternator. And so we've succeeded in producing a sine wave from the rotational frequency here. So this is very common with wheel speed sensors on cars and airplanes, so that all four wheels can rotate at the same speed to prevent skids. Typically, when the slip and skid differential is exceeded, in other words, you're making too sharp a turn at too high a speed, one of the wheels is going to spin a lot faster. So if you're going straight at, let's say, 80 miles per hour and you suddenly turned, the right rear wheel will spin a little faster to compensate for the decrease of the front left wheel, usually if it's on the drive line. And so that's conservation of energy once again. Something has to go down for something to go up, etc. So to compensate, then it goes into a skid. So the goal would be, a good practical application is anti-skid vehicle technology. So each one of these wheel speed sensors, they're like 4-channel sensors. They're wheel speed sensor per wheel. So originally they were kind of like 2-channel, and they transversely pick up wheel speeds. But today we have all this 4-channel independent wheel speed sensing. And so that wheel speed sensor, if you look at the little teeth, there's a little air gap, and that behaves like an AC generator. So whatever the application is, it could be a wheel speed sensor, or it could be an engine's flywheel. You hook an alternator up to it, I keep saying alternator, AC generator up to it, and you get the sine wave. So if not a pure conversion of the wave, that would be in various power of wave equations. You have a few that are electromagnetic, a few that are mechanical, like for sound. And so you'd have to derive that with the differential equation, or just look up the formula for whatever wave. So this would be an electrical sine wave, an AC electrical sine wave. And so at this point it's irrelevant, because we're not going to do much with this wave other than use it to sense data, other than any mechanical usefulness, right? Because we already have that going on here. So you may want to know the torque, RPM, brake horsepower, etc., for fuel controls, etc. Or it could be a wheel speed sensor, or it could be a constant speed propeller that's electronic, etc. And instead of using a hydraulic propeller governor, you're using an electromechanical or even a software-based mechatronic system. But it can all start here with having an alternator connected to this drive, and then the certain wave, sine wave, is harnessed, generated. So we're translating the energy with respect to information. So one cycle is one revolution of this rotor, and so at 600 we have 20 of these cycles, and at 600 RPM, and then at 2000 RPM we're having 66 of these cycles in 1 second. So again, it only takes, let's say, a 2000 RPM 0.015 seconds to make one cycle, because that's 1/66. And so to translate what's going on with this rotor, the amplitude, positive and negative, would represent the radius of the rotor. So whatever that registers on the metric, the measurement, would describe the radius. So you may have an out of round condition, or you may have excessive wear, and you may be wondering, how did your car know all of this information about the structural and mechanical aspects of your car? Well, if you had an out of round condition or missing material below the tolerance, this amplitude would drop a little bit, and then you get a little red flag, a little yellow triangle with an exclamation mark in it. It's all because of this amplitude drop. So this is pretty much supposed to be constant. And then, of course, the RPMs is the frequency. So if this was a wheel speed sensor, all three of the wheels would have to slow themselves down to the slowest wheel, and that would avert the skid, because there's a limit. Some people want to go like 130 miles per hour and make a sharp turn and see if the anti-skid catches up, but there's a limit, right? There's a limit to how much you can do that. So it's within a reasonable performance curve, right? So it's pretty responsive today with the computing power. So there'd be a secondary high pressure ABS booster, not just for anti-lock but anti-skid, that would kick in and then graduate a pulsation on those three wheels to match them to the slowest wheel, because the sine wave graph for the three wheels is going at a higher frequency RPM than the others, and so it's just a matter of slowing that frequency down by high pressure secondary automatic braking, like pulsation. And so it happens so fast with the computing power and the software, but it starts here with this little AC generator translating a sine wave from the mechanical. And so the next is the wavelength. This would represent the torque of the rotor. And then, of course, the frequency is the RPM. Amplitude is the radius of the rotor with respect to the plane of rotation. And then if we multiply the frequency, hertz, times the wavelength, we would then get the speed of the wave. And this translates to the angular speed, or the circular speed. So if we took pi d circumference and then we multiplied it times the number of revolutions per second, we can get the linear, or we can get the circular velocity with respect to pi d times revolutions per second. That would just be the speed of this wave going through. And so that is could be translated to the transmission and or the linear travel. So every time you rotate this wheel, it's pi times d, the diameter times pi, and that's how much linear distance you would get on the road. So this waveform could also tell you your road speed, including the wheel slip, including the wheel hops and all this type of stuff, right? It's very subtle, but if you look at car value estimates in NADA, they often ask you your zip code and location, and one might say, what does it matter? It's the same car, but there's a statistical curve on how many wheel slips and hops and everything occur. And today, now, this can be GPS broadcasted back and forth, so really, I don't think that's relevant anymore, but there is a statistical coefficient of tire rolling resistance and kinetic friction that translate to what your actual road wear is with all the wheel slips and hops. So it could be picked up here, and then sometimes there's like a standard established that your odometer will only pick up what you actually had wear at, so nobody's got to argue about zip codes and locations anymore. So that's another consideration. It's in the software. You could write a code to pick all that up and equalize it. So they made it easier, and it's easier and more accurate, right? So again, when you talk about wave particle duality and all sorts of fancy words, all we're talking about is the conservation of energy. And in this case, since it's a practical application, it is the relationship, in this case, mechanical to electrical. Now it could be mechanical to thermal, It could be mechanical to sound. It could be electrical to heat or thermal. It could be electrical, whatever. But in this case, I felt that this particular practical example would be something everybody could relate to, because more than likely, you've had a wheel speed sensor problem and you plugged in your OBD2, and it will tell you it might have a sine wave graph on there somewhere in the diagnostics. So that's all this is. It's just a lot of millions, billions of these little digitized like a digital version of an AC generator on board, and that's usually in the position sensor, or it could be in the crank sensor, and then it's converting it over into a sine wave for interpretation. And this could be in the wheel speed sensor. It could be in anything. But if we wanted to get really fundamental, we could go like, this is the subatomic particles, or we'll just say it's the electron spin, and then there's a certain waveform, a frequency. So if we went to the oxygen 2 gas, diatomic oxygen, just oxygen gas, O2, it's got a 60 gigahertz frequency on its waveform. So that means one divided into 60 billion would be the time period. It'd be some insane, decimals of nanoseconds for a period, but it's still relevant. It's still relevant and relative, because if this was a subatomic particle, let's say electron, proton, the electron is exiting, the electron is exiting, so it's in the negative, and then the proton's entering, it's in the positive, electron's exiting, and then it's proton. So really it's information, it's not really a particle. The electron out, proton in, it's all information and energy. But when it hits this neutral point, the trend line, that's when it becomes the neutron, and then it becomes the physical particle. So this is the same thing going on. It's just in the very fundamental. So where would you find this? Well, in light, you would, you can't weigh light. It has no mass, but it does have particles in it. The wave particle duality of light. The photon is this wave of light, but there's an entanglement that happens as the proton, or as the electron exits, and the proton enters, exits. And remember, when we say exit, we're talking about grounding information and energy, and then receiving it, proton, sending it, electron, proton receiving it. And when we go back and for 60 billion times per second, we're going to hit this neutral trend line that becomes the neutron, and that then becomes the mass component of, let's say, the oxygen gas molecule, right? But if we scale this up from quantum to classical, it would be correlating to, a rotor spinning mechanically, something you can touch and work with, tangible. So it's not quantum, it's classical. And then here's a correlating waveform to this rotation. So it doesn't matter if you're dealing with planets, galaxies, black holes, or you go all the way down to the subatomic components in the quantum sense. So this, I think, is a very important fundamental, because when you reach a project or your assignments or your homework, there's going to be a lot of language and symbols that seem to maybe throw you off. It's like, what in the heck is this? And then, university is about self-teaching. You're a researcher. Nobody's going to do your work for you, right? So the professor's job is to not do his job. His job is to tell you something that's not really true, because if you're a qualified researcher, you're not going to go by hearsay. You're going to go by mathematical analysis, right? So each to their own. It is, I guess, survival of the fittest. But those that are teaching, they're going to be fundamentals. They're going to be teaching a fundamental approach. And of course, you're not going to reach students if you're starting out with all this woo-hoo stuff that is real, but you know, it's just like that's what they're getting in their assignment. They wanted some help. So having, you know, teaching physics, teaching engineering for several years, I've used this example in university, college environments, and it's been very receptive. The correlation between something mechanical you can touch, let's say rotation, orbital mechanics, and the electrically interpreted equivalent sine wave, like an AC sine wave. So we'll just say this is a not a standing wave. This is a Hertzian wave oscillation, but it's more with respect to the voltage or the velocity or the RPM. So that might be a question that comes up, you know, is this a parallel or a series AC generator connected to there? And because we're able to change the frequency of that wave, means we're able to change the velocity of the wave. So it is not going to be a parallel circuit, it's going to be a series circuit. So we'll assume that we have some constant torque, i.e. constant current, and then we're able to change the RPM. So you can think fundamentally like this. So if you end up getting one of those questions where you're designing a sensor or even doing the stress analysis, and right away they say series, you're going to be like, nope, that's a constant torque, constant current, because energy is not created or destroyed. So what happens to what's correlating to current? It's going to be the torque. What's correlating to voltage? It's going to be RPM. So in this case, we have a series wired AC generator, and it's then mapping a voltage sine wave that is variable. So we'll just keep the torque as a constant. That would be the C, or that would be not to tell you the speed of the wave, but the constant, the C versus the V, the variable versus the constant. So everybody thinks a little differently. But if you end up with a Schrodinger's problem, or even a Heisenberg problem, or something that has to do with spin, polarity, spin, quantum number, etc., it shouldn't bother you at all, because you're like, hey, there's a frequency, electron out, proton in, it's all energy. But when they reach the quantum entanglement, this trend line, we then have the mass component of that energy, the neutron state, and that's what these elements are. So of course, oxygen doesn't tell you anything. Is it a gas? Is it a liquid? Is it a solid? But gaseous oxygen is always O2, and so you may have to work on electrophysics for solid oxygen research and development, or solid oxygen matrices, I'll put it that way. But still, you can do it through the waveform once you get the frequency of the element and or the frequency of the molecule. So if we're doing the frequency of oxygen gas, then it is definitely 60 gigahertz. And of course, you can pair that with spectral analysis and then run the radio frequency or digital communications, wireless communications through that spectrum. And so that is something that people have known as 5G, 60 gigahertz. But in non-military applications, the 5G is not really practical. You really can't use 60 gigahertz outside of military and hospital applications. Military medical, that's it. So it's about 29 point something in the real world. So that's the 5G. And so you'll have to do your homework and find out which elements or elementals or electrochemical matrices reflect 29 gigahertz. And you can do so now because this practical application has made the correlations. Thank you for watching this video and have a great day.